So we're in section 5.2. Moving right along. We want to write down some probability rules. So we have to use probability notation, which can be a little bit troubling or confusing at times. The notation looks like this. So if the event is represented by some letter like A, B, C, D, E, F, then the probability of the event is written P parentheses on each side like this. You stick the event inside there like that. So if we have some more complicated event like A or B, where A and B are events, the probability A or B is written probability parentheses A or B inside. There is something they use for events called complement. We'll be talking about that later. The probability of A complement would be written P parentheses with A complement inside. So what are those types of things? A or B is a set of outcomes belonging to A or B or both. So you might know what that is. You might know that's the union of A and B. Sometimes you write it like this, A union B, like that. A complement is a set of outcomes not in A, but in the sample space. So it's everything besides the outcomes in A. That's the definition of that. So that's written other ways. Sometimes it's written like this, A complement, like that with just a prime on it. But ordinarily it's something that looks like an exponent, but it isn't. That represents complement. And then later on it'll be A and B is the outcomes belonging to both A and B. And sometimes that's written intersection like this, A intersect B. If you've seen that before, then that would make sense to talk about it now. Over here, we'll say events E and F. Now I've given up an A and B, now I'm an E and F, but it's the same story, A, B, C, D, E, F. We're going to be talking about disjoint events. They're disjoint if they share no outcomes. And for these types of events, we have the addition rule for disjoint events. Now we're combining these ideas together. The probability of E or F, if E and F are disjoint, is the probability of E plus the probability of F. So let's see, we have to look at an example of that happening. The example is, here's the random experiment. Randomly select a token labeled 0 through 9. So each token has probability of 1/10 of being chosen. There's 10 tokens. 0 through 9 represents 10 tokens, so there's 10 tokens total. They're equally likely, so each has probability of 1/10. And then we'll set E be 0, 1, and 2, and F be 8 and 9. This is a Venn diagram. Of the outcomes. So here I've got the sample space represented by this rectangle, and the outcomes sitting inside it like this. Sometimes you draw Venn diagrams with the actual outcomes in place, and sometimes you just draw them abstractly using these ovals representing sets. And then if the ovals overlap, then we consider them to be sharing outcomes. This is disjoint. They share no outcomes. Here's series 0, 1, and 2 belong to E, 8 and 9 belong to F. None of these belong to both. If I had drawn it differently and 2 was in both of them like this, then they wouldn't be disjoint anymore. We're going to verify the addition rule for disjoint events by computing the probability of E or F. E or F are these 5 outcomes. There's 10 outcomes in total, so the probability of E or F is 1/2. And then we look at E and F separately. E has 3, so its probability is 3/10. F has 2, so its probability is 2/10. And lo and behold, 2/10 plus 3/10 is 1/2, but that seems like it's pretty clear, because if the events are disjoint, the number of outcomes in the union is the OR is the sum of the number of outcomes in the two events separately, because they don't share any. Since they don't share any, the total number of outcomes is the number of outcomes in E plus the number of outcomes in F. And so using the number of outcomes to compute probability, the probability then becomes the probability of E plus the probability of F, because the outcomes add. Now we can extend this to more than 2 outcomes. Say you had 3 outcomes, E, F, and G. They don't share any outcomes. So these little circles indicating the events, the outcomes belonging to the events have no overlap to them. Then the probability of E, or F, or G, E, or F, or G, the outcomes belong to E, F, or G, or all of E, F, and G in any combination. Since they're disjoint, it's just the outcomes in E and the outcomes in F and the outcomes in G together. The total number of outcomes is the sum of the outcomes in each, and so the probability of the event that involves all their outcomes will be the sum of the probabilities of the events E, F, and G separately. Same type of picture. And so that lets us write at least something down that's a rule. It says for disjoint outcomes, the probability of the or the union is the sum of the probabilities separately. And we've been using that rule kind of implicitly for a while because we're looking at probabilities, say, for individual outcomes. If you think of individual outcomes as representing events, then the probability of 0 or 1 happening would be the event. Sorry, the probability of 0 or 1 happening with the probability of the event 0 or 1. So it has 0 and 1 in it. Is the probability of 0 plus the probability of 1. We've been using that as we've been going along. For simple events that involve one outcome alone, they'd have to be identical events to share any outcome, so that the idea of being disjoint is a lot simpler. But with events that involve multiple outcomes, then for them to be disjoint, they can't share any outcomes, and that can happen easily just if they share one of many outcomes that belong to those events. So we'll look at some more examples of this in a minute, but right now I've got to clean the board like usual, and we'll see you in a minute.